Okay, now what happens when we take into consideration the CGD? So the model will be a little bit different. So we will have something like this. And it will be CGS, CGD, GM, BGS, out, and CL here. So that will be the circuit that we will have to analyze. And before going into the analysis, we need to study something that is called the Miller effect. So for the Miller effect, when we have some amplification, in this case it can be a voltage amplifier, and we put an impedance. It can be an impedance, but we are going to assume that we have a capacitance here. We connect an input voltage here, V in, and it will produce a V out here. We have that V out is going to be equal to minus VA in. Okay, and then we have that there is no current flowing in the voltage amplifier, as we saw that the ideal model is infinite impedance the input, so all this current has to flow like this. So this input current here, this input current will be equal to the V in minus V out divided by 1 over G omega C. We replace the output here, we have a minus here, so there will be minus A times V in, all of this omega C in will be equal to V in 1 plus A, and then this goes up, G omega C. And then if we want to find the impedance that I see in this direction, theta in, that will be equal to V in divided by E in. The voltage that I have divided by the voltage that appears here. So we divide V in divided by V in, that will be equal to 1 plus A multiplied by G omega C. Now this is a very important result because at the beginning we had only one capacitor C here, but when I put it in the middle of an amplifier between the input and the output, it looks like this capacitor is actually C times 1 plus A. So it has been amplified, this capacitance, when I see it from this direction. Okay, when I see it from the other direction, on the other hand, we have minus A okay, so then we have we can call it V test here. When we see it in this direction, there is no amplification here, and what we actually see as impedance, okay, we have 1 over G omega C, is the output impedance of the amplifier in parallel to the capacitor. Okay, that will be the impedance that I see in this direction. Okay, so there is no amplification of the of the capacitor when I see from the output, but from the input it gets amplified. Okay, with this background we can come back here and then we analyze the first case when we have a small value for CL, and then the first thing that happens here is that it is going to appear a right hand zero at GM divided by CGD. That is because there is a direct path from the input to the output that will create this zero, and this zero is a very high frequencies. CGD is small, GM it is very small value, so the 1 over GM that will be the effective resistance, it is quite small, and the capacitance is very small. You will put the right hand zero very far away, close to FT. Okay, CGS, CGD are not so far away, so this is going to be close to the FT of the transistor. And then we have a pole at the input. The pole at the input will not be anymore depending only on CGS, but it will be depending on this capacitor that has a Miller effect. So the whole value of this capacitance will be equal to CGD 1 plus the low frequency gain. Low frequency gain, as we calculated before, the intrinsic gain is minus GM times R out. The low frequency gain that depends on the transconductance and the resistance. The pole at the output will depend on CL and depend on the capacitance. The capacitance doesn't have any Miller effect, so it goes directly here, and that will be the positions of the two poles. That is for small CL. Now, what happens when we have a large CL? So when we have a large CL, the position of the pole will change. If we have a very large CL at high frequency, it will short the output. So, or in other words, the impedance of the capacitance here will dominate, and the gain of the amplifier will not be the same as at low frequencies, and then the Miller effect will vanish. Okay, so for very large capacitive loads, there will not be this Miller effect. So what we have is that the pole at the input will be approximately RS 1 divided by RS CGS plus CGD without the Miller effect, because this gain doesn't apply anymore. And the pole of the output is going to be the same. Then we have a last case that it is we can have a very large CGD, a small CL, and large input resistance. Okay, and this particular case, it is actually quite common in analog integrated circuit, because there might be many cases in which we have the following connection. For instance, common source amplifiers connected in cascade. Okay, so RDS of this first transistor can be very high. It might be that we have a current source instead of the resistor. It can be very high, so it might be that we have a very high source resistance here. So if we model this again, the more better and applicable model for this will look like this: RS in parallel to CGS, CGD, and then we have GM times VGS, and then we have RL, and in parallel to the capacitor CL here. So that will be a much better model for us. Okay, now before we go forward, I think it is instructive to analyze what will happen if we have the following connection. We call it a diode connected transistor. Okay, and for very low frequencies, if we have a gate, we have drain, small signal model will be GM VGS. This is the source, and then we short circuit the gate and the drain. VGS. We try to find what is the impedance that I see in this direction. I can connect a test voltage here and calculate the test current that passes, and then I just divide VT divided by IT. So think in this particular case VT is equal to VGS. That means that this current IT will be equal to GM times VGS, which is equal to GM times VT if we replace, and the VT divided by IT will be equal to 1 over GM. Okay, so when I short circuit the gate and the drain, the resistance that I see in this direction is equal to 1 over GM. So this is a very interesting result that we're going to use right now. So now I'm going to simplify my analysis here. I'm going to assume that this resistance, it is very large, very large, and then I'm going to find the resistance that I see in this direction. I will call it an equivalent resistance that I see in this direction, and then I'm going to disregard this. I'm going to assume that this is a very large impedance. Okay, so I'm going to move to another blank page here and redraw the circuit. So if I just take that part of the circuit, that will look like this. We have CGS, we have CGD, we have GM times VGS, and then I will calculate what is the impedance that I see in this direction. So for that I connect a test voltage source, and then I will let the current to pass here. Now here we have a voltage divider. This voltage divider to calculate VGS. So we have that VGS will be equal to 1 over G omega CGS divided by 1 over G omega CGS plus 1 over G omega CGD. All the G omegas disappear. This is times VT. So then I will have 1 over CGS divided by 1. We can already work here. So that will be CGS times CGD, and then I will have CGD plus CGS. This will go, and then I will have CGD times VT divided by CGD plus CGS. Okay, and then for we can calculate the current that passes here. the current that passes in this direction. That will depend basically on this current here and the current that flows here. So I'm going to separate. I know that the current that it is going to flow here will depend on this series capacitance. This series capacitance is a C equivalent that I will call it. It is just a parallel combination, CGS times CGD divided by CGS plus CGD. And then for this one, I need to calculate the current that flows down. That will be GM times CGD divided by CGD plus CGS. That will be that current goes down times VT. And if we just disregard for a second the capacitors, that we know what is the impedance of those, it is the series capacitance, and then we just take this transconductance that is here, that will be equal to the test current. Then we have that the test current, the test voltage divided by the test current will be equal to, or that will be 1 over GM times CGD plus CGS divided by CGD. So, okay, so then this one, this is going to be this part here. This impedance I will call resistance equivalent here. Okay, so and then if I go back, okay, if I go back to, we can see here that 1 over GM, it is the impedance assuming that it is totally short circuit, but if it is not totally short circuit, we have a factor that depends on the capacitances here. Okay, so if we go back, to our maybe we can still here that we have a space. So we have that the output pole will depend on this equivalent resistance on this equivalent capacitance. So the output pole will be located approximately in 1 over, and we have something big here, and then we have the equivalent resistance. This equivalent resistance, it is 1 over GM times CGD plus CGS divided by CGD. Okay. This will be in parallel to R out. Multiplied by the capacitance. We have the total capacitance that we have. We come back to our model. This is R out here. R out and CL. So we have in our model CL plus, and now we will have to add the capacitance here, the equivalent capacitance. That will be CGS times CGD divided by CGS plus CGD. Okay, that will basically be our output pole. So it has moved, and then 1 over GM, normally it is much more smaller resistance than the R out. RDS it is much higher. So if the resistance goes down, it means that the pole has to be pushed to a higher frequency. So if we do the limit, we can do some simplifications here. We take this one here. this one here, we can say that the output pole is equal to, and then this is 1 over ft. Okay, so this is the omega t of the transistor. That will be omega t. Okay, this is omega. We put omega t tgm divided by cgs plus cgd. So we have omega t there. We disregard the out if this is much more smaller, so if it is in parallel, so this disappears, times, and then we have that for this factor, if CGD is very large in comparison to CGS, this disappears also, and we simplify these ones. This is very small, basically disappears. This will be approximately this goes to the denominator, the CGD, and then we have the rest that it is CL here plus CGS. Assuming that CGD is very large, then we can just simplify CGDs and assume that it is very little, it's almost zero. And then we have the following equation for the output pole: omega t CGD divided by CL plus CGS. Oh, that is what we have here, with a minus sign, of course. It is in the right, it is in the left hand side. Now, what has happened here? The input pole, we have a Miller effect. The output pole, it has moved to a higher frequency because, as I mentioned before, this is much more smaller than this. That means that small resistance. Then, at the end of the day, what we have is that the first pole, if we assume the position of the pole without a very large CGD was here. When we increase the value of that capacitor, we add that capacitor, it will move to a lower frequency. And the second pole, the output pole, on the other hand, will move to a higher frequency. So if we put the plots in the pole zero diagram, we will see that they split. Okay, when the input pole moves to the lower frequency and the output pole moves to a higher frequency, we say that they split. They are splitting the poles. However, when we calculate the gain pole product, the result is almost the same, because one pole goes to lower frequencies, the other go to high frequency, kind of compensate each other. So the amplifying capabilities, when we calculate with or without CGD, they really don't change for the common source amplifier. They are exactly the same. Okay.